Hi everyone, welcome to Math's Spellbook. I'm your host Peter, and basically we're going to continue our journey through the world of numbers and probably get into some functions while we're at it. So I will be joining up with my friend Sascha. Sascha. So basically, let me just get him on. So just bring him in here. Hey Sascha.
Hey, what's up?
What's up? So let me just get the link for you so we can start sharing. But how are you doing today, my friend?
Good.
Okay, I just sent you the link.
Oh wait, I think I clicked on the wrong thing.
Let's see here.
Let's see.
Do you want me to try to send it to you again?
Yeah, but I mean I got the link, but I got a canvas that's already that already have stuff on it.
Oh, whoops! I think I sent you the shareable version. I sent you the just sharing.
Yeah.
So I'll just resend you that.
I mean, usually Escalator is not very happy if we write too much on it, so I think we should take the habit of starting with a new one.
Oh, okay.
Is that one good? Or is it this one? Oh, this one is empty. Alright.
Okay, let me see if I can find you. Trying to see where your arrow is at.
I think you have like some kind of disc on the right corner, top right corner, with like some names.
Oh, that's us. That's on Discord.
Yeah, but no, not on Discord, on Escalate Draw.
No. Like those discs are basically our icons because for some
Yeah.
For some reason, I think like Windows, when they did an update, they basically are making like, or when Discord updated, they're probably putting that on like all like Windows like machines, I think, or something. I don't know.
Oh, but they have like other names on Discord. For example, your name is Careful Partridge, or something like that.
Let me see.
I see you now. Okay, bon.
Oh, okay. Oh, this is the other one that
Yeah.
we did. Not you, but like another one of our fellow friends that were trying to teach me more. I think it was Mavort that was trying to teach me this stuff.
Oh, okay.
I didn't realize I took you to this one.
Okay. I mean, this one look empty, but yeah.
Yeah, it's filled with a lot of stuff actually.
Is it?
I mean, for me, it looks like it's filled with a lot of stuff.
For me, it looks very empty.
Oh,
Wait,
okay.
I moved to somewhere where there's stuff written.
Yeah, I'm moving down where there's no stuff written down.
Okay, yeah, I think it's good then.
Okay.
Okay, hopefully.
I think we've opened
All
so
right.
many of these that it's left like work a lot. So.
Yeah. So, okay, so today our goal is to define function.
Mm-hmm. Oh, we're
And,
already going into functions already. Okay.
Yeah,
we were
that's
still
kind of
on
weird
numbers.
because, yeah, actually you need function and you need a relation to be able to define the other number. So yesterday we basically went through Zermelo-Frankel axioms.
Mm-hmm.
I mean, it was very painful, but we had.
Yeah, I was reading a
Good
bit
one.
like this morning about relations. I went into the last part of the proof of the book of proof book, and like it was covering like relations, and I didn't realize that like less than or less than to equal to were relations. Like
Yeah.
I didn't know that, and I was like, oh, that's what relations are. I mean, I don't
that's
know.
pretty-
I don't know the formal definition, but like, I mean, like on stream, I'll just briefly just show it. Like, basically, they define relations as the first part. So, I was like, oh, interesting. And I think this is before they go into real analysis proofs a little bit, because they cover it like in the online version of the book.
Yeah. So that's pretty good. You see relation because function will just be a.
Well,
special
I only
case
saw
of
like a
relation.
brief look at it. I didn't look at the formal definition yet.
Okay. So let me start with. Okay, first of all, we need some construction, which is the Cartesian product.
Okay.
Okay. And pretty much you would have two sets. Let's call it A and B,
A and B, right?
because that's our favorite names of set. A and B sets. Then you can build another set, which we usually write something like A cross B.
Uh-huh.
Which
So that's
will be,
that's how you pronounce it, right? A cross B.
yeah, or
Okay.
A times B. I mean,
Oh, you can even say times it, like multiplication?
yeah.
Oh, okay.
And what will be the set? The set will be order pairs. So this is not like sets usually don't care about order.
But this one does.
This one does.
Okay.
Where A is an element of big A and B
Is an element of
is an
B.
element of big B.
Okay.
So this is the pair of. So this is the set of order pair. So example, if we do an example, I don't know. Maybe we can look at. Well, I'm gonna cheat. I'm gonna use stuff that we haven't seen yet, but I mean, we are somewhat familiar, even
Okay, the
informally.
integers and the real numbers, okay.
Times the real number. So what will be the set? It will be the order pair of. Maybe let's put an n for an integer, and maybe let's put x for a real number.
Okay.
Where n is in some kind of integers and x is some kind of real numbers.
Okay.
You go. So for example, the pair 4 pi would be something that live inside of the Cartesian product of z with r.
Okay.
And also you have also abbreviations. So for example, you probably have seen many times people talk about R2, right? So this is just a short notation for R times R.
R times R. Yeah.
Yeah. So this is the order pairs of real number.
Okay.
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 So just to be sure we're talking the same thing. So for example, the element 1, 0 inside of R2 and 0, 1 would not be
Be the
equals
same. Yeah, they're not the same because the order is different.
the order matter. Okay. Okay. So that's kind of the intuitive pictures of it, and there's not very much to it. But we just have, if we want to be honest with ourselves, we have just something that we haven't defined.
Okay.
What on earth is order pair?
Okay.
Because in set theory we just have basically the thing I showed you yesterday. We have set, we can
Set
take
and
union.
elements. Yeah.
Yeah. So we need a way to define what is another pair. Usually we will not use it much, but we just need to know it exists. And let me show you one implementation of it, which I just stole from Wikipedia.
So, question before you move on, do we need a special set of axioms to define, I guess when we move on to sets of numbers to functions, or we don't really need to develop axioms for those?
No, we don't need any more axiom in mathematics. No, we have all the keys to build whatever we want. No.
Okay.
Which is a bit mind-boggling to think there's only 9 axioms.
This is why Sascha's here, guys. He's basically teaching us how to build mathematics.
Okay, so what is the order pair? So one definition is you will consider it as the set.
Yes.
Which contains 2 elements, or maybe sometimes will just contain once. But the first element will be the set that contains only A. By the way, I don't think I've said that yesterday, but a set that contains only one element is called a singleton.
Wait, say that again?
A set. I will write it below.
I'll bring it up for you guys.
So maybe I will just put a note that contains only one element. It's called a singleton.
Singleton. Okay. So basically that means there's just one element, right? Nothing more? Okay.
Yeah.
Is that the name of the set that just contains one element only? Disregarding the empty set?
Yeah, the empty set is not a singleton because it contains nothing, but yeah.
What about a set that contains the empty set? Would that be a singleton?
Yeah, that would be a singleton.
Oh, okay. So you can include the empty set in that. Okay.
Yeah. You just have to have exactly one element.
Okay. That's something I don't think I read about. Okay.
So this would be the definition for an order pair.
So it has A and the set A and B in a set.
Yeah.
Or element, I mean.
Yeah. And the idea is so this is built of 2 sets.
Yes.
So if you look at this set and you found a singleton, then it will correspond to the first element.
So since the order matters, so the singleton, does it have to be the first of the pair?
Well, I mean, when I write this, the order doesn't matter.
Oh, the order doesn't matter. So
wait, okay, maybe I'm confusing a thing. What do you mean by order? Do you mean the way I've ordered these guys on the right, or you mean the guys on the left?
The guy on the right side, you have a singleton of A, but you don't have a singleton of B. So my question is that, and since that is a definition of an ordered pair, right? My question is that since you have a singleton of A, does that mean that if you're going to have an ordered pair, does that mean you have to have a singleton of the first, the first number of the pair? So in this case, you have A as the singleton?
Yeah.
But why is it that you don't have B as a singleton?
Because I want to be able to distinguish between the AB, on the left, with A first and B second, and I would like to be able to distinguish between a BA.
Okay.
So if we look at BA, what it will be using this definition, it will be B, AB. All right.
Oh, okay. Okay. So
And
basically, the one first is usually the one that's in the singleton. Is the singleton? Okay.
Yeah, exactly. That's the point. Yeah.
Okay. Okay. Okay.
So it allows you to distinguish between A, B, and B.
So the order doesn't matter because like since we have like BA in this case, right? You didn't have to write BA for the second set after the singleton of B, right?
Yeah, because the order doesn't matter, right? Because this guy is a set on the right.
Okay, so basically we
A,
still
B, or
write them
BA
as
is the same thing.
we still write them as sets, so the order doesn't matter. But like the ordered pair itself within the parentheses is what matters. The order matters.
Yeah.
Okay.
And the way as you said, the way you're able to distinguish between which one is the first and which one is the second is the first is inside of singleton.
Okay.
So, okay.
Mm-hmm.
We will not use this definition, but we need at least a way. If we want to be honest, we need just to.
So just like one last question, and like to save time, you can probably answer it in one sentence if you can, and if you can't, then basically just say we'll move on. So would it be safe to say that since we have an ordered pair, right? Let's say if A is an independent variable, right? Would it be safe to say is that saying that every time when you do an ordered pair and the independent variable is always going to be first, it will always be the singleton in the ordered pair set? Is that safe to assume, or that will not always be the case?
Well, it doesn't really make sense, right? Because you said it was the singleton would be the first in this set, right?
Right.
But this set does not have it does not know what order is, right? So it does not make sense to say that this guy is before this guy, right?
Okay.
Because set doesn't care about
order.
Yeah.
Okay.
I feel sometimes like sets are a bit like teenager. They don't care about much.
Oh, okay. I see. No, I'm just asking. Maybe I'm getting ahead of myself.
Yeah.
It's because we're so used to thinking of ordered pairs as like independent variable, and the second one is the dependent variable. So my idea is that if it's in the singleton, then that means it's going to be the independent variable, and I think that's just basically where my mind was going.
Yeah, you were sort of thinking about function.
Yeah.
Yeah, but the Cartesian product is kind of bigger than the function.
Okay.
You will see that the function is just a subset of a Cartesian product at the end of the day.
Bonjour, poison mouse.
Okay, so let's define a relation, okay? And you will see it's very simple.
Okay.
So let A and B be sets.
Okay.
In set theory, everything is a set, so maybe I should stop writing. Let's say B be sets, but anyways.
We're correcting as we go. Don't worry.
So a relation on A and B.
Okay.
Is a subset of A times B.
Okay.
So, in other words, a relation will usually be called R. Because that's kind of obvious.
Yeah.
And it will just be some subset of A and B.
Okay.
I know you might say, well, that's just a subset. Surely that must not carry a lot of structure, right?
Mm-hmm.
So I will give you some example of a relation, okay?
Okay.
So I'm gonna take an example that you probably, everybody knows. We're gonna take A and B to be the both the real number, okay?
Okay.
And I will take my relation R to be, obviously it would have to be the ordered pair of R times R, in other words, R2.
Mm-hmm.
And I mean, I'm gonna use the thing we saw yesterday. So you remember, I can build subset of a set using the set building notation with the axiomatic schema. And what will be the relation? It will be X
subset of Y.
Is smaller than Y.
Oh, it's smaller than Y. Okay.
Yeah, sorry, maybe my.
No. I just didn't see it pointing. Storm says in the chat. Let's see. When you write empty, it is a set with one element, which is the empty set. If you want to have just empty set, you need to erase the parentheses. Okay. I'm guessing you basically saw our beginning portion when we were asking about the simpleton Storm. But thank you for pointing that out.
Yeah, so Peter was asking if the empty set was a singleton. I said no, but if you put the singleton inside of a set like that, you get a singleton.
Yeah, I kind of figured because I know an empty set with the parentheses around the empty set is not the same.
Yeah.
All right. So y is less than or equal to, x is less than or equal to y, right?
Yeah.
Okay.
So this R here will be exactly the definition for, that's kind of, okay, this thing is kind of circular because I use the less on equal to, but I haven't defined it. But okay, maybe I can do something a little bit better. I don't really like my example, so I will change my mind, okay?
Sorry.
So maybe I can say A and B to be
the
natural numbers. Yeah, it would be a bit easier.
Okay.
And I can say what's the relation I want on them. I want the relation to be there exists some S, which is some natural numbers, such that Y is equal to X plus S.
And there exists a Y that's an element of, is that U or W?
That's a natural number, I'm sorry.
Oh, natural numbers, oh, okay.
Yeah, my N is not very clean, I'm sorry.
No, it's okay. There
you go.
Okay, so S is a natural number and X plus S, and okay.
So the way you have to think is that Y is basically X plus some extra stuff.
Right.
Plus some positive quantity.
Okay.
And if you have an element of these guys, usually when you have a relation, so if X is inside of a relation, it doesn't matter what relation is, but we will usually write something like that.
Okay.
X is related to Y.
Okay, yeah, I think I've seen this notation before. I thought it was kind of strange because I've never seen I guess a capital letter basically in between two variables.
Yeah. But usually you can use a nicer symbol for that. Usually you don't want to use R. For example, here I will use a very basically the symbol will tell you the whole thing. I will use this notation instead of the R.
Okay.
And you probably just by the use of notation I use, you can probably tell what is this relation, right? So this is exactly the definition of being less or equal to something.
Oh, okay. It's just in mathematical notation in this case.
Yeah, that's the definition for a natural number.
Oh, okay. Yeah, I've never seen that before actually. Yeah, the way they define it this way. Since you're writing it like a set, right? Could you also because you have n cross n, right? Can you also change that to say n to the 2?
Yeah. Yeah.
Okay. I wasn't sure if that was mathematically eloquent to do that.
Yeah. Okay, so I have here to introduce some kind of warning, though.
Okay.
We have to be careful. So usually in math, when people write something like A2s, they means 8 times A.
Yeah.
Okay. And the world would be fantastic if everybody was using this convention. Unfortunately, people in topology and geometry have some kind of bad habit.
Which is?
For example, For example, people. I mean, I will basically just give you the definition. So, for example, people might define the circle something like that, right?
Mm-hmm.
So maybe we can say it's a point inside of R2, such that I mean, some norm or some distance, is equal to 1.
Okay.
And you can define it, and what people will usually do is they will define SK to be
P is an element of R.
K plus 1.
Plus 1.
So they can define sphere of a higher dimension, right?
Uh-huh.
But here's the catch, though.
Yeah.
S1 cross S1 is not
S2?
Is not S2.
Oh, okay.
So sometimes you have to be a little bit careful.
Oh, okay. So basically it's just safer to write the cross right here, right? Like N cross N, right? That's what you're basically saying, right? Okay.
Yeah.
That's fair.
So you have to be a little bit careful, for example, when you're talking about sphere. Usually people would denote, for example,
depending upon what branch of mathematics you're dealing with, right?
Yeah.
Okay.
I mean, that's kind of one famous example of sloppy notation
see.
used in mathematics.
Storm type 2 things. One relation you use since you are a child is x parentheses x y. I forgot what the curly line means in math.
So it probably, I mean, I don't see the chat, but it probably means equivalent.
Okay, it's equivalent to AB, and I think also it implies both ways that XB equals AY for X, Y, AB, and Z. This relation represents exactly fraction, and it.
Oh yeah.
And you obtain all the rational numbers, which is equal to the the integers to the second. Okay.
Yeah.
But what is the line and the equivalent symbol mean?
So there will be some kind of relation we're gonna see. So right now I just introduced relation as just some subset of Cartesian product, but you have a lot of type of relation if you want. You have, like, for example, ordering relation, you have equivalence relation, you have like functional relation.
Yeah, and the second thing, and the second thing Storm type is it's just to have the dimension as a manifold, and here the K is the dimension. Okay, thank you for your input, Storm.
Yeah, usually what people should probably write, I mean, at least if they want to be a little bit more or less ambiguous, usually they will put parentheses on the top for the dimension.
Oh, okay.
Yeah.
That's based on your experience, right?
Yeah, but for example, Jean-Pierre Sartre, which is a French mathematician, who is very, like, he really wants people not to abuse notation, usually writes sphere as SK with the K being in the lower index.
Oh, Storm is an algebraic topologist.
Okay. So he's part of the bad one. Nah, I'm kidding. Well, in topology, this thing on the S1 times S1 is usually T2.
Okay.
Which is a torus, the two-dimensional torus.
Oh, okay.
And you don't want to mix them up in topology.
Oh, okay. Alright, so we were and the less than symbol, and it's a definition, so
I mean, usually with abuse of notation, you're fine. I mean, I use this abuse of notation all the time.
It's just a warning. It's just a little bit of a to keep in mind. Yeah, I get it.
Yeah. Just want to be more transparent. Okay. So let's talk about today. I want to cover two types of relationship.
Okay.
The first one would be functional relationship.
Okay, functional relationship.
And basically, functional relationship will be the definition of a function. Okay.
Mm-hmm.
So, I mean, I have a bad habit, so let A and B be said. R is called So let's R be some relation. I mean, as far as we know, relations are just subset.
Okay.
But we don't want them to be anything, right?
Right.
So if we want to define function, I mean, something you probably heard in high school is you have the vertical line
Vertical.
test, right?
Yeah. Yeah.
So if we want,
test, yeah,
so maybe I can just give the options. What we want to define is we want to define what it means to have a function from A to B. And basically, if you just think about what is a function, it's basically an assignment from that takes some value in A and give you some output in B, right?
Right.
But this assignment must be unique. Okay, they must. I mean, for example, a little A, they cannot be many. They can only have one B that you can assign. So we say R is a functional relation. Oh, sorry for the scribble.
Sorry.
Relation.
Let's see. Storm typed. Equivalence relations are the most useful in my opinion. Almost everything is defined by the equivalence relation. Oh, okay.
Yeah, we're gonna use them to define the integer. I mean, that's what we would like to do like to do today.
Okay.
So so what we want for a functional relation, we want that for all x inside of A. Also, this point will vary a little bit if you look at some textbook, but I will explain the difference. So you want for every x in big A, you want that there exists some pair. Okay, maybe I can just. Okay, maybe it will be a bit weird to write. Okay, let's see. There exists some pair inside of R in a relation. Such that P is given by XY, where Y is inside of B. Okay. So this first condition basically imposes that you have to choose one element of B for every element in A.
Okay.
So you cannot have, like, for example, a partially defined function. You cannot skip value inside of A. You have to.
So everything in X, or in this case, everything in A, has to give an output. That's basically what you're saying. In B. Okay.
Okay. And the other condition is the vertical line test. So I want. If I have xy1 and I have xy2 inside my relation, I want y1 to be equal to y2.
Okay.
So basically, this guy you can think of as the vertical
line test.
Yeah. So it basically ensures that every x there's only one output.
Yeah, because like x is like treated, I guess, as is it treated as the same x in this case?
Yeah.
Like because you didn't write a number near it, it's just basically just x in this case.
Yeah.
So for y1 to equal y2, it basically has to be the same x that equated to like y1 in this case, right?
Yeah.
Okay.
And usually this relation, we usually, use the usual notation. We usually write f as A to B.
Okay.
Where a relation, if you want, we can call it f, but we usually write this as.
So before we continue, I noticed that you wrote we say R is a functional, right? So I'm guessing this R is supposed to be the relationship R, right?
Yeah, so it's a functional relation.
Okay, so my question is that like I don't know if you done calculus of variations. Like,
Yeah.
is that the same functional that you would do in calculus of variations, or is that a totally different functional?
Well,
By definition.
Yes. So a functional in functional of
Calculus of
calculus of variation has another meaning.
Okay, so it's different from that type of function.
Yeah.
Okay.
Yeah. I mean, it will still be a function, but it has to satisfy some nice property. Yeah.
Okay.
Usually, it will be some like continuous map into R or something like that.
Okay. I just wanted to make sure of that, so I didn't mix them up, because I haven't learned calculus of variations at all yet.
Yeah. But right now we're kind of like at the very basic level, right?
Yeah. That's why I'm trying
calculus variation is like kind of up there. We don't have. I mean.
Yeah.
We don't even know what real numbers are yet.
Okay.
So this.
Gotcha.
So function are just a map, are just relation like that.
Okay.
And you can do it with any set. I mean, I can just maybe like some funky set. I don't know. Maybe we can have the set of what can be A. I don't know, colors maybe.
Mm-hmm.
Red, blue.
Oh yeah, Sascha, the assignments that you basically assigned for us, right?
Yeah.
Are those going to cover all the topics that we discussed for this week that you plan out? Like each of those problems, or were all those problems meant based on the first lesson?
For this week.
For this week, okay. Got it.
Yeah, actually there is very little thing from the first lesson because we haven't done much. I mean, we did a lot, but it was more like formal stuff.
Got it.
I mean, it's more today that we can play with stuff.
Okay.
And let's be some, I don't know what you like.
Mm-hmm.
Maybe some Pokemon.
Why not? Yeah.
Okay, I have to admit I don't have a huge culture in Pokemon, so I will use
Pikachu.
Is that how you spell Pikachu? Is that how you spell it?
Let me help you. Oh, whoops! I meant to click the eraser button.
Okay, fine.
Pikachu.
Yeah, there is no T. Okay. Okay. Well, I don't know much Pokemon. So...
Actually, we'll go with what Storm suggested. I'll write it down for you. So Charizard and Squirtle. All right.
Yeah. Is there like a green guy?
Oh,
like a throw leaf.
Oh, you wanted
Bulbasaur,
4?
yeah.
Bulbasaur? You wanted 4?
Yeah, I mean, that's fine. I thought the team was Fire Red starter Pokemon, but I guess Pikachu is not a starter. So.
No, you went to the yellow version ahead. It's okay, it's okay. Alright, continue.
Okay, so we can do a map from A to B.
I'll just help you with this one. Yellow. There we go.
So if we want to be very formal, we would say, well, the function is order pair. So maybe, I don't know, we can take. Well, I guess yellow is kind of Pikachu, so we're gonna assign yellow to Pikachu.
Mm-hmm.
Well, there's no red for Charizard, so I'm not sure which color we should take.
Oh, yeah, I'll do that for you. Okay, red, and just erase that. Just erase that.
Charizard, and wait, Squirtle green?
Oh, Squirtle's blue. I'll take
that. It's like the turtle-like, right?
Yeah.
Yeah. Yeah, I only play one Pokemon game in my life.
No, that's the same with me. I just watched the show. That's how I know.
And I was a Bulbasaur user, and pretty much I was spending my whole games just make all the Pokemon sleep and then suck their HP.
I mean, like I haven't heard that many people talk about Bulbasaur a lot, so I'm like, you're the first.
Yeah.
Usually it's either Charizard or Blastoise, and I'm like, okay.
Yeah. So why is this thing a functional relation? Is because first of all, for all color we assign something.
Yeah.
See, we have red, blue, and so on. And also for each color, we assign only one, right?
Right.
One Pokemon.
Yeah.
If for example we have yellow, which is assigned Pikachu and at the same time Charizard, then it will not be a functional relation.
Okay.
Okay. But usually I mean, I don't know any same people that write a function like that. Usually what people do instead is they write as, I don't know, yellow is equal to Pikachu, f of yellow is equal to Pikachu, and f of red is equal to Charizard. Yeah, I'm gonna butcher all the names, I'm sorry.
Don't worry about it, I'll take care of it. Oops.
Okay, and now I just want to give some warning again.
Okay.
Because usually people will call something which is not a function in our case.
Okay.
For example, people might write f as a map that goes from R to R.
Yeah, I think I'm familiar with that scene in books.
And they will write something like that, right?
Oh, yeah, 1 over x, right?
Yeah.
Yeah.
But then you get a problem, because for x equals 0,
it's undefined.
This is undefined. So f is not really a function.
Oh yeah, and also it has a asymptote, right?
Yeah. So yeah. And the problem why it's not a function is because it's not defined at x equals 0, right?
Yeah.
That's the issue. I mean, that's not very a big problem. What you can do is you can just define another function. And to fix the issue, you just have to remove 0, right?
Storm says, but f from r star is 1. I'm not sure what that means.
Yeah, I mean, if we define on r star, which is r while we remove the origin, now it's well defined.
So wait, what does r star mean?
R star is just a short notation, so maybe I can write it. So r star is the set of all real numbers such that x is not equal to 0.
Oh, okay. So the star, like, what does the star signify?
So, okay, the star can have a little bit of different meanings. Sometimes it will means that you have, I mean, if you have a set where you have like some notion of 0, for example, the integer or the natural number, you can maybe put a star and say, well, I want all the natural number which are not 0.
Oh, okay. So does that mean that star basically signifies a set as long as it doesn't include 0? But everything else?
Sort of, because there's like another use of the star.
Oh, okay, okay. So it depends on which branch of math we're talking about, right?
Yeah, I mean, it kind of depends. Sometimes the star is used to signify the invariable elements.
Oh, okay. Okay.
So yeah, this is unfortunately like people use this notation in 2 different ways, and you have to make sure that which one people are talking about.
I see. And thank you for the raid, Zach. You can continue on, Sascha.
Okay, so you see sometimes function stuff that people call function are not really function. They're like partial function in the sense that if we shrink a little bit the domain, we will get something that is defined everywhere, but on the whole thing it will not be a function. So this f can be sometimes referred as a partial function.
Welcome, Raiders. Welcome. I'm Peter, aka Matt Spellbook. Welcome to Sascha's lecture on functions. So basically, like 1 over x is considered a partial function, like you said, right?
Yeah. Okay. If you look from R to R, you would say it's a partial function. And what's the definition of a partial function? Well, it's the same thing as a function. It's just the first axiom can fail.
Let's see. Oh, okay. The first axiom can fail. Okay.
Yeah.
Oh, okay.
So maybe it's not. Yeah.
Actually, Zach, how was your stream? I'll just ask that quick before we continue. But carry on, Sascha. Sorry.
Actually, in French, we have like kind of 2 words for function.
Really?
Yeah. So a function in French, I mean, it's not universally used, but it's used at least in Bourbaki, which was very influential in French mathematics.
Yes.
A function will usually mean a partial function, so it may not define on all its domain. Okay. And if we want to stress the fact that the function is defined on the whole domain, we're gonna say it's an application.
Okay.
But in English, we don't. I don't think you really have a word that do this how to distinguish the two. But usually when you read French mathematics and say an application, or in English it's basically an application, but it's kind of not very a word you would use for that. It just means it's a function that is defined everywhere.
I see.
But for us, we're gonna use the word function to mean it's defined everywhere, and sometimes we'll be a bit sloppy and refer as 1 over x as a function on R.
Storm. I think Storm is also French because they said in French we call it application instead of function. Okay.
Yeah.
All right.
But it's not always. We don't always follow that. Like some people.
It just varies.
Yeah, some people use application in a sloppy way also. But,
All right. So where were we?
That's like a end-going word in mathematics.
Yeah. Okay. So we have a partial function, which is like 1 over x. So where are we gonna go from here?
Okay. So this was just a warning that sometimes. Thing that people call function are not really function according to the definition, but
okay.
You can still usually get around just by shrinking your domain to something.
So it's considered a partial function, not an actual function itself.
Yeah.
They never explained that in school, actually.
Yeah. But you see, the difference is kind of subtle, right? Because a function is relative to what you define on, right?
Right.
Like on R, it's a partial function, but on R star, it's a completely fine function.
Oh, so it's like depending on the context of where it's
defined.
Yeah,
it depends on the domain, right? Because the point of the thing we had on the top is that it's not defined on 0, but if we remove 0, now it's completely well defined.
Okay.
Okay, next a thing we can do with function is composition. Composition of 2 functions.
Yeah, Storm also said you could define everything with factor if you want.
Okay.
Composition of 2 functions, right? That's what you wrote?
Yeah.
Okay. And also chat, let me know if you can't see certain things and I'll just like move around just in case. And if we do get cut off during stream, I am also recording this lecture, so like if we have too many cutouts in the stream, I will upload the lecture just in case.
So if we have 2 functions, we can build another one from out of those 2. If the domain accord with the image, so we can do a g after f, which will be a function that goes from A to C.
Okay.
So usually it's a good idea when you do composition to write diagrams. So usually you do, I have my A, I have my B. Oh, my B is not very good.
I can help you with that.
Yeah.
I'll erase that.
Yeah, my handwriting is terrible, guys. my B and my D are so like
Yeah.
bad.
Yeah. Like probably for future reference, like if you do future assignments, maybe like we can wait. You can actually like try to type it up if you think it will be easier for you.
Yeah, I mean typing is kind of taking too much time, so I don't really want to do that.
Oh, okay, that's fine.
Okay, so we have F and G, and what we can do is we can compose them.
Okay.
We can form G after F.
Okay.
And basically what you're gonna do is you're basically gonna take, so you're gonna take some little a here.
Mm-hmm.
You're gonna take some FA here, so you're gonna get some output. And what you're gonna do is just you're gonna feed it to J. That will be G after F.
Okay.
And if we want to be extra formal, what we can say is G after F. I mean, if we think as a relation,
Mm-hmm.
it will be it will be all the pair AC inside of A times C, such that what would it be? Well,
Is that A and C or A and B?
A and B. I mean, here the notation is kind of weird because I'm treating F as a subset of A times B.
Okay.
Like in the formal definition, but I mean, usually we will not write I mean, nobody will write something like that, obviously. So usually people will just say G after F is you take some X and you just define as something like that.
Oh, okay. So when it's written like F, like the dots and A to B, right? That's still like that's kind of considered as a subset. Is that what you're saying? Of like A and B.
Yeah. So if you want to be very, formal, yeah, it will be a subset of A and B.
Oh.
I mean, but this is like kind of crazy formal, right? Usually people will just write stuff like that instead.
Oh, okay. Yeah, because that's something new to me. I never heard of that.
Yeah.
Which kind of makes sense though, because like it's actually taking from the set A and going on to B. So I'm thinking, oh yeah, that does make sense that I guess the function is a subset of the two.
Yeah. Okay. Usually, so maybe I can just distinguish something. Usually, when people want to refer at this thing living inside of A times B, they don't usually write F. What they do instead is they write. Wait, is that the thing in English? I just have the word graph, but I don't think is graph a word in English?
Yeah. Graph is a word in English. I think
graph of a function is yeah. So usually they will use the word graph to denote the order pair inside A times B instead of F.
Mm-hmm.
I mean, that's usually how you avoid the confusion.
Oh, okay.
Okay. Okay, and for this week assignment, I have to introduce two notions.
Okay.
And pretty much like half the assignment for this week will be to play around with those concepts and prove stuff with it. Okay.
Mm-hmm.
So we call.
Mm-hmm. Go on.
So if we have a function from A to B, we say the following. So so this is basically an adjective for your function, is injective if for all x and x inside of A, if you have f of x is equal to f of x prime, you have that x must be equal to x prime.
Okay, I remember you writing this in the assignment sheet.
Yeah. So this is like one-to-one, into injective. That's all the synonym.
Mm-hmm.
And you also have surjective, which is something similar. So what it says is that if you have some if for all y inside of B, you have that there exists some x inside of A, so that f of x is equal to y.
Okay.
So basically, the surjective is the word that people use is onto, which is a word that people use. So basically, what you have to think is that every element inside of B is, has some input that's mapped to it.
So this is onto.
Yeah.
Right? And I think injective is like 1-to-1, right?
Yeah.
Okay.
And F is a bijection. If F is both
Injective and surjective, right?
Yeah.
Let's see. Poison Mouse said all elements have image surjective. What does that mean exactly?
I think he was just like anticipate. He was ahead of us on the defense of a surjective.
Okay.
I think. I mean, I don't have the chat.
So like I remember what you told me about like the differences. Like I think like a while ago when I was streaming, like you said that basically like with an image, it's basically based off the function, but if it's a codomain, it's based off the space.
Yeah.
That function is like going on. Is that correct? Okay.
Yeah. Okay, so there is also the word that people say. So F has a left inverse.
Yeah, this one's when I read this part out, this was something new. I've never heard of a left and a right inverse.
If there exists a G that go from B to A, such that F G after F is equal to the identity on A.
Okay.
Okay, maybe I haven't defined what is the identity. So the identity is just. Huh?
Yeah, like I remember looking over the notes you wrote, and I didn't see any definition about identity.
So identity is a very simple function. You just go from a set to itself, and it do the most basic thing you can imagine. It just takes X, whatever you give as an input, and just give you back the input.
Oh, okay.
So it's like a very basic function. And the left inverse just means you can find some J that give you the identity when you compose on the left.
So, like, when you say that, that means like if we were to do, I guess like the composition, you're basically saying the left identity is basically we would get G in return.
Yeah, so you can find some G that will, when you compose on the left, you will get the identity. I will give you an example of a function that you know, so you can.
Okay.
So we say it has a right inverse if there exists a G that go from B to A. But the definition will be, I mean, basically backward. We're gonna have F after G, and this, I mean, if we start from G, so G start at B and F go from A to B. So this thing is go from B to B. So instead of asking we have the identity on A, we say we have the identity on B.
So hold on. So if there exists, Is that a G or a Y? That's G,
It's a
right?
G.
Okay.
Yeah.
Let's see. Poison Mouse said the codomain is equal to the image that surjective.
So maybe let's give you an example.
Mm-hmm.
Okay, so example, I want to consider the function f that go from R to the positive real numbers, okay?
Okay.
And this function will be x. You can write that, but you can also write. Maybe you're more used to the third notation.
Yeah.
But the second one is actually is the same thing. So you just take x and it map it to x squared, right?
Mm-hmm.
And you can check that this map is on 2, right?
Yeah.
Because every positive real number can be realized as some square of some real numbers.
Mm-hmm.
But it also has a right inverse.
Okay.
So what would be the inverse in that case? So let me be. So basically, what we want to do is undo the squaring. So what we're gonna do is we're gonna take the square root.
Square root. Yeah.
And now, so if it has a right inverse, it means if I compute f after j like that,
Mm-hmm.
I should get the identity. So if I give it x, I should get back. I should get that x.
Because I guess with computational math, we would think of f as squaring it, but then since it's g, which is the square root, basically it will just square the square root, thus giving us x back.
Yeah, exactly.
Okay.
So maybe we can do it. So I will. So it's going to be a good example of composition, right? So
yeah, it's a good review of pre-calculus.
Yeah. So what we do is we use the definition of this guy. So this guy is just f on which we apply
g
of x. Yeah. Now what is g of x? Well, we said it was the square roots.
Right. So it's f of the square root of x.
Exactly. And now what is f doing is squaring it.
Right. And thus giving us x back.
Yeah, because x was positive, right?
Yeah. So the left inverse is just basically going from, going from the inverse to the original function, whilst the right inverse is basically going from basically using the original function to that is actually using the inverse function to basically get x back. Both of them get x back, but in different ways, right?
Yeah.
Okay.
Yeah. So one way is you have a map from A to B.
Yeah.
You can think it maybe as a transformation or something.
Mm-hmm.
And if it has a height inverse, then it means you can. If it's a height inverse, it means you can undo it.
Okay.
So if you take something which is inside of, if it has a left inverse, it means if you take something in A, you can undo this transformation to get back the original thing.
Okay.
But in the other direction, you basically can do the same thing, but for B, then it would mean it has a right inverse.
And this has nothing to do with, say, uniqueness or anything, right?
No, so you can have many right or left inverse.
Okay, got it.
But this week exercise, so you kind of see that this map is on 2.
Which one? Oh, the square? Yeah, the actual square. Yeah.
So this map is on 2 and also right inverse. That's no coincidence. You will see that if you undo it means you're onto if and only if you have a right inverse.
Okay.
And you're into if and only if you have a left inverse. And when you are bijection, which means you are both,
Yeah.
then you will have a right and a left inverse. And furthermore, this inverse will be unique.
So, like, let me just summarize of what you just said, right? So, it's so this is 1-to-1, right? That's the first thing you said, correct?
Yeah.
So it's 1-to-1, and we have a right inverse, right?
So maybe I can just write it down below. F is injective if only if F has a left inverse.
Is it only a left inverse?
Yeah.
Interesting.
F is surjective if and only if F has a right inverse. And F is a bijection.
When it has both?
Yeah. And in that case, so if you just have left inverse or right inverse, you might have many inverse.
Is there proof of this, or is this just an axiom we just take for granted?
Oh, that's the assignment of this week.
Okay. That's the actual assignment, right?
Yeah.
Okay.
So the hard part is if you have an injective map to show that you have an inverse.
Okay.
Which is like the hardest part. But in the note I gave you, I already did one of the case. I did like this part. I showed this implication.
Oh, the injective part?
Yeah, imply left inverse.
Okay.
And basically you have to use the axiom of choice, which is like one application of it.
Yeah.
And the other direction, if F has an inverse, then F is injective is not too bad. You just have to play a little bit, but yeah.
Okay.
As an inverse. So when I wrote an inverse without specifying which one is left or right, this means both.
Both. Okay.
So it means it exists a G that goes from B to A, such that F of G is equal to the identity on B, and G after F is.
So can you present like examples of each? Well, we already presented an example of surjective, right?
Yeah.
Can you present an example for injective and bijective?
Yeah.
Okay.
So okay, we're gonna take F to be. Oops. Maybe I can take it that go from Z to Z.
Okay.
And the map will be, we take X and we map it to 2 times X.
Okay.
This map is injective. Okay. So the way you prove that is you say, okay, let's suppose I have 2x, so I have f of x and I have f of x prime, which are both equal, right?
Right.
So what I'm gonna do is I mean, what is f? So we said f was
It's 2x.
So what I have the following equation, right? But now what I can do is I can just cancel out the 2, right?
Right.
This is one property of the integer. You can cancel out the non-zero constant. So I get that x is equal to maybe I should just put implies. I get that x is equal to x prime.
Okay.
Which is by definition mean that f is injective. Okay.
Okay.
But this map is not surjective, right? Because
no, it's not.
Because it maps to a positive integer. So for example, it will never map to 1 or 3, right?
Right.
But not surjective. But actually there's a trick to make it surjective. Right? Because if you look at the definition of surjective, what it says is that every element inside of the of the codomain is obtained by the image of something in the domain, right?
Mm-hmm.
So what we can do is we can shrink that thing. So for example, instead we could consider the function that go from f to 2z.
Okay.
Okay, so 2z is just the even integers.
Okay.
And we can take the exactly the same formula we use. We can say f prime is just x is equal to 2x.
Mm-hmm.
But now this map is surjective. Because it's clear if you have that every even integers can be realized as an integer times 2, right?
So wait, what was the trick that you did to make it subjective in this case?
I just made the codomain smaller.
The codomain smaller.
So in the previous case, my target was z, right?
Oh, so basically when you did multiplied by z, like by 2z, right? You're just basically limiting the amount of integers to use, right? Because it has to be defined that way. Okay. No, because like when you said smaller, I was like, wait, aren't you multiplying everything by 2 in that case? But then I'm thinking about the outputs, and I'm like, oh wait, there's gonna be a limited amount of. I mean, it would still be like an infinite. You can pair each output together, right?
Mm-hmm.
But at the same time, it's considered smaller because you're using less numbers in that case, technically.
Yeah, exactly. Right? Yeah. Okay. Yeah. So 2z is contained inside of z, so it's smaller.
Yeah, because it would be like 2 times 1, which is 2, and then like 2 times 2 would be 4. It limits the amount of numbers you're getting, right?
Yeah.
That's what you meant by smaller, right?
Yeah.
Okay.
Smaller as a set, so it's a smaller subset.
Right. Okay.
And pretty much you can always do that. Whenever you have a function, you can always make it surjective if you make the codomain smaller.
Okay.
But now this map is surjective, and the constraint to be injective does not really care about what domain we map to. It just care about it basically care about those kind of equations, so it has nothing to do with the codomain. So this map is awesome.
So you made it smaller to basically kind of like help trick it so we can make it subjective, but why is the act of making it smaller like needed in this case? Like if you need it smaller, like what does that cause? How does that cause that to be subjective?
Just because the condition asks that every element in the codomains are hit by something in the input, right? But if I make the target smaller, so I'm restrain those things.
Okay.
I'm able now to hit all those all those elements.
Oh, okay.
So here you kind of see something that we probably haven't thought if we were in high school and just doing a manipulation of symbol. Yeah. So f and f prime are defined with exactly the same formula, right?
Right.
But one is onto and one is not, right?
Yeah.
And the reason is because the notion to be onto or surjective is dependent on what we're mapping to, right?
Oh, okay. So you basically made it smaller so you can make it onto something instead of just one to one. Okay. Yeah. That makes sense.
So this map is surjective and injective, so this is bijection.
Okay.
We're gonna see a bit later that there's also a trick to make a function injective, but it's a little bit more complicated. Okay, before I go to equivalence relation, I just want to define other stuff. So if I have a function that go from A to B, and I have a subset of A, and I have a subset of B, I can define the following. I can define f of A, which is going to be a set inside of B. It's going to be all the y's inside of B such that there exists x inside of big A, inside the, oh sorry, I didn't mean to use A. Here I'm supposed to be using X. Yeah, that's on me. Such that f of x is equal to y.
So is the x in f of x, is that the big X or is that the small x?
That's a small x here.
Okay.
So usually we call this the image of x by f.
Okay.
And we also have something dual if you want. We have f minus 1 of y.
Mm-hmm.
So just to be sure, this guy is a subset of b.
Okay.
And this guy will pretty much do the opposite. So what he's going to do is going to be a subset of A. So it's going to be all the x inside of A.
Okay.
Such that f of x is inside of big Y.
All right. And I'm guessing that's a subset of A.
Yeah. And usually this thing is called the pre-image. Of Y.
Is it because it's using Y instead of X? Like it's using Y as the input while the X is the output? Is that why it's called the pre-image?
Yeah.
Oh, okay.
So maybe I can just write an example, and after that we're gonna go to equivalence relation.
Mm-hmm.
So, for example, if I want to map okay, maybe we can have the following map. Well, I guess we can take Z. And I will take multiplication by 2, okay? We just take x and we multiply it by 2.
Mm-hmm.
And our x can be what's
So
our x?
so it's from F from Z to Z, right?
Yeah.
Okay.
Maybe x can be 3z, which is the set of all multiple of 3. Okay.
So X is the is that supposed to be 3Z? Like X is equal to 3Z?
Yeah.
Equal to... Oh, okay.
The set of all multiple of 3s.
Okay.
So now if we look at f of x, so for example, if we take just an element of x, so an element of x would be would have the following form, right? It would be like, I mean, maybe you can write something like that, right? It would be 3 times some integers, right?
Mm-hmm.
So if I want to look at this image, I'm gonna get 2 times that, right? So
And n is supposed to be an integer, right?
Yeah.
Okay.
So I'm gonna end up with 6n.
Uh-huh.
So, I mean, basically what this shows is that if we start with something inside of x, if we look at the image of, if we look at the image of 3z, what we end up is we always end up with something which is divisible by 6, right?
Uh-huh.
So at least the image of that is contained inside of the multiple of 6.
Oh, okay.
Actually, you can show that actually this is equality. Okay. And the reason why, so, okay, I haven't teach you that, but I think it's important here I show you. Okay. So here what I want to show is I want to show that the image of f of 3z is equal to the multiple of 6, right?
Right.
And as you said, as you saw yesterday, if we want to show that 2 sets are equal, we just have to show they have the same elements, right?
Right, yeah.
So usually the strategy is to show that we have both inclusion.
Okay.
So here you see with the computation I did on the top, I said, okay, let's take some Or yeah, I should put it exists. I just said should probably just let 3n to be some arbitrary element of x. I showed it was a multiple of 6, right? So I showed this inclusion.
Okay.
Starting with something in 3z, I get something in 6z when I apply f. And if I want to show the other direction, I say, okay, let I don't know, 6m be inside of 6z, right? Just a multiple of 6.
Yeah.
Now what I can do is I can say, well, okay, so 6 can be written as 2 times 3, right? Times m. So what I'm gonna do is I'm gonna take these guys as my input. So consider x0 to be equal to 3m, okay? Do you agree with me that this is inside of 3z, right?
The x naught part, right? X is equal to yeah, because it's 3 is a multiple of 6. I mean a divisor of 6.
Yeah, but I mean here we don't have to check it's inside of 6. We have to check it's inside of 3, right?
Yeah.
So here we agree with something. It's a multiple of 3 because it's 3 times another integers, right? So if we look at f of x0, so what we get by definition, so it's f of 3m. So f what it does is just multiply by 2, so we get 2 times 3 times m. So we get 6m, which was our initial
condition.
Yeah, that was our initial thing, right? Maybe we can call it y, I don't know. So what we show is if we take any element inside of the multiple of 6, we can always find something in the multiple of 3 that got mapped to this number. So what we showed here is we showed that the multiple of 6 is contained inside of the image, inside of this. But now we have the 2 inclusion. So previously we showed this. We showed the backward. We showed this. But if you have both,
yeah,
this implies you must have equality. Okay. So that's a pretty standard strategy if you want to prove equality between sets. You just show that you have the 2 inclusion like that.
Like proving both sides, right? From like basically from y and from x, right?
Yeah.
Okay. Let me just take a look here. So it's an element of x, and then let y equals. Oh, okay. So basically, you do one to equate to the other, and then basically you do the other one equate to its inverse.
Yeah.
In some way. Okay.
Yeah. Sometimes it can be a little bit harder, but I mean, usually to prove equality of set, you just show inclusion.
So the image and the pre-image, right? So the pre-image is basically from y to x, whilst the image itself is from x to y.
Yeah. So maybe we can have a look at pre-image. So let's say our function is the map from R to R. Oops, not R2. I'm sorry.
Alright.
And let's say it's x squared.
Okay.
And let's say we want our set y to be a singleton. It's gonna be I don't know, a square.
Okay.
Okay. So let's say a is
greater
is
than
not 0.
Okay.
Yeah. I mean, it doesn't matter. You just have to say it's not 0.
Okay.
So what will be the pre-image of that?
Of a square? The pre-image. So if it's from y, if it's pre-image, then basically it'd be like the square root of a, right? Oh no.
Okay, so let's maybe.
I'm thinking of a function. Sorry. Because basically if it's like f of that, so because then it's supposed to equal to the x part, right?
Yeah, so basically what it will be is all the real numbers that are mapped to a square. So maybe usually when you're stuck like that and you don't remember it, you just write the definition of pre-image.
Okay.
That's usually what I like to do when I'm stuck. So so here what I'm gonna say, okay, what's the pre-image of that thing? It's all the x inside of R such that we have x squared is equal to a square.
Okay. So this is the definition of a pre-image.
Yeah.
Okay.
I mean, usually in the definition, I mean, okay, maybe I cheat a little bit. Usually in the definition I wrote on top, I would just say x squared is inside of a square. But as this thing is just a singleton, it just basically just I mean, this definition is equivalent to check that x squared is equal to a square.
Oh, so there's two ways to write it then.
Yeah.
Okay.
Because if x squared is inside of a square, it just means that x squared has to be equal to a square, because there's only one element inside of this guy.
Right. Okay.
So now we are with something more familiar. We want to solve the equation x squared, which is equal to a square. So I mean, at this point we all know how to do it, just algebra. So what we're gonna find is x is
equal to a.
Well, there is also another one, right?
Positive a and negative a.
Yeah. So what you see here is that the pre-image of a square is not just one thing; it's two things, right? It's minus a and a. If we take a to be equal to 0, then the pre-image will only be one thing, right?
Yeah.
It will just be 0, because in that case, positive and negative are the same thing.
Yeah.
And if, for example, I look instead of the pre-image of, I don't know, minus 1, what would it be?
It would be two answers again.
Are you sure?
Yeah, because like whenever you square a negative number, it becomes positive.
Well, okay, let's write the definition. So the pre-image of minus 1, by definition, it would be all the x inside of R that verify that x squared is inside of the singleton that contains minus 1. In other words, we want x squared to
equal negative 1?
Yeah.
Oh, okay. Yeah, which it can't.
Which it can. Yeah, exactly. So in that case, the pre-image is empty.
Is the empty set if we're using real numbers in this case?
Yeah.
Okay.
Yeah, for complex number, you would have something else, right?
Okay.
Yeah, but what is important is if we go back in the top, we said that f was a map from R to R. So the pre-image will be the empty set. If we were working over the complex number, now they will have like two other roots. It will have I and minus I.
Okay.
But yeah, was it a little bit enlightful?
No, it's insightful, yeah. Because like now that you mention it, when I was like, oh, okay, like. So this is like the definition of the pre-image, and basically if it was y, the element of the real numbers, then basically it would be the image, right?
Yeah.
Okay.
So usually when you get question and you're stuck, usually it's a good idea just to
write the definition.
And you rewrite the definition, right?
Okay. Yeah, that makes more sense actually. Actually, yeah, this is a good way to relearn inverse of functions. Because I was never taught this way, and I'm like, oh, okay, this makes it a lot more I mean, it's more technical, but it feels more elaborate. So yeah, I think this is like pretty informative.
And also,
yeah,
you can see that the inverse of a function. So usually we're a bit careful between. We made a distinction between the pre-image and the inverse of a function. So as you can see, for example, we're still writing f minus 1, right?
Right.
Which you might think is the inverse of a function in the sense that you have f times f minus 1, which is equal to the identity or something like that, right?
Yeah.
But here it's not the case, right? Because our function is not even a bijection, right?
Yeah.
And you can clearly see this at this point, right? If we look at this example, here we get two things that get mapped to a square. So f minus 1 cannot be a function because otherwise it would have to assign two values.
Right.
To this a square. So this map is not. The f minus 1 is not a function.
Oh, okay.
You can just only talk about pre-image, and that's something people get wrong sometimes.
So you're saying basically the pre-image is not a function because like it uses two numbers, right?
Yeah.
And what was the other point that you made afterwards? Like,
so if you have a bijection, people will usually so you say we have a bijection.
Yeah.
I mean, one of the exercises of this week is to show that the bijection is a function that admits a left and right inverse, right? So we have g of f is equal to the identity, and we have f after g is also equal to the identity. Okay. And usually when we have an inverse, usually we call g f minus 1.
Oh, okay.
And this will be a function. But you have to be careful because the f minus 1 here is not the same that we see here. Okay, the f minus 1 for a function, the first one we have here.
Yeah.
You can always make sense of that. The second one you cannot always make sense of that because you need to have a bijection to make sense of that.
Okay.
But the two are related in the sense if you look at the pre-image of a singleton, then you will just get the f minus 1 in the you will just basically recover the second definition.
Oh, okay.
And the pre-image will just be a point.
Okay.
So you see here we have two values in the pre-image. That's actually show that f failed to be injective.
Okay.
Because we have 2 points here.
Yeah.
So the minus a and a are both mapped to a square.
Because it's 1 to 1, and basically it requires like one specific input to actually make one specific output. But this one we have two. Okay.
We have two. So it's not injective. And here you can see that f failed to be surjective.
Yeah.
Because, for example, minus 1 has no element that maps to it.
That goes to that set of numbers.
Yeah.
Okay.
So f is neither injective nor surjective.
Okay.
So usually when you think about function that's not injective, you can think about those examples.
Okay. Yeah, that makes sense.
Yeah. Sometimes it's funnier because I ask you in some exercise to find some counter examples, so you have to play a little bit with the function.
All right.
Right.
So what's next?
So what's next is the equivalence relation.
Okay.
So a relation. So again, A and B are set. So we have R, a relation on A times B is called an equivalence relationship. So, I mean, I will use the notation we used before. So A is related to B. If we have the following properties, okay? And what you have to keep in mind is basically we want to copy the property of equality.
Okay.
So we want we want A to be related to A.
Okay.
And also usually when we talk about equivalence relation, we usually replace the R by a little squiggly line like that.
Oh, okay.
So we want, and usually we don't say A are related to A, we say that A is equivalent to A.
Oh, okay.
So this part is called reflectivity. I don't think I can spell that. The second part is called transitivity.
Okay.
Well, actually, no, actually, it's not actually this part yet. So if we have A which is equivalent to B, then we have B which is equivalent to A.
Okay.
Which is like kind of symmetric.
Oh, okay.
So, example, if you have 2 which is equal to X, then you also have X which is equal to 2. And the last property is transitivity. So if you have A which is equivalent to B and you have B which is equivalent to C, then you have that A is equivalent to C.
Okay.
So the most famous example is, I mean, the simpler example is spelled with the A in English, is equality. Let's say equality of sets.
Okay.
So of course every set is equal to itself. I mean, the definition of equality for a set was like they must have the same element. Surely A has the same element of A.
Yeah, we're back to Russell's paradox.
If A is equal to B, well, what it means for two sets to be equal, but it means they have the same element.
Yeah.
So of course B has to be equal of A. And if A is equal to B and B is equal to C, well, that means that A has the same element of B, and
yeah, and then A is equal to C.
Yeah. So of course that's an equivalence relation. I mean, that's kind of like that's kind of the prototype example, right? Now I'm gonna introduce two equivalence relation, which will be important for us. Okay, one is a kind of a toy which I put in the exercise, but I will not do it all the way because it's part of the exercise.
Yeah, it's part of the exercise. Yeah.
Yeah, that's like the last exercise of the
sheet.
Exercise.
Oh, so that's like number exercise 5 then.
Yeah.
Okay.
So let n be. Oh boy. Be some integers. We might assume that n is positive because I mean it doesn't really change much. Then as we already used the notation several times, we can look at nz, right? What will be this thing? It will just be the multiple of n.
Okay.
I mean, nothing surprising here.
Yeah.
But this guy defines an equivalence relationship on Z. Want to see how? We say that X is equivalent to Y with this relationship if X minus Y is inside of NZ. Okay.
Okay.
Okay, let's maybe do a very simple case to see what is going on. So let's n to be equal to 2.
Okay.
So what we're saying is that if we have two numbers, we so let's maybe what it means. So what it means, we will have x minus y, which is equal to 2n for n some integers, right?
Okay.
But here, what I want to stress out is this thing is just a fancy way of saying that x and y have the same parity. Okay.
Oh.
So let's take, for example, I don't know. Give me two odds number.
Hold on, Sascha. I think you were writing some stuff, but I think some stuff didn't get written in.
Oh. So what's the last thing you see on the board?
So basically it says, like, say x is equivalent to y, if y minus y, and then there's a big space. After that it's z.
Oh yeah, you're missing like 3 lines. I guess are we? What we can do? I guess we do another escalier draw.
I mean, like, do you see it on yours, like what you wrote?
Yeah, maybe I can actualize. Yeah, we'll reload my page.
Should I just refresh? Should I try refreshing mine, or?
Well, wait, hold up. Yeah, you can.
Alright, let's try that. Oh, no.
Wait, where's the content now?
Trying to go down.
Oh, it's down.
Dang, I don't see it. Oh no.
This guy is not happy.
Yeah. Yeah, I think it's all gone. Oops.
Oh no. I mean, it's not too bad because we can basically just look up at Wikipedia for the definition.
Yeah, and basically the VOD is still like recording, so, and streaming
Yeah.
recording, so yeah.
Yeah, we're good. Okay.
Yeah, so.
So I think we're just gonna do another escalier draw.
Okay.
Okay, how do I make a new one though? Open. Not save to disk. Well, I guess it's gonna be easier to use in incognito. Okay, there you go.
Do I have to join yours? Like, since you probably re-uploaded the stuff that you wrote?
I haven't. I'm just gonna rewrite the thing, yeah. But I'm sending you the link.
Okay.
So while you're joining, I will just rewrite the thing. So we. Oh my God, that's some thick. That's some thick stroke right there. Wait, am I like too zoom? Oh yeah, I'm like 169%. All right.
Okay, there you are.
So let n be some positive.
Sorry about that, guys. Technical
integers.
difficulties.
We said that x is equivalent to y if x minus y sits inside of nz. And what I wanted to do is the case n equal 2.
Mm-hmm.
So basically what you're saying is that x is equivalent to y if x minus y is equal to n4. Maybe I shouldn't use n, let's maybe use k instead. K is some integers.
Okay, there we go. Yep.
And basically what this thing is saying,
Uh-huh.
in clear term, is that x and y has the same parity.
Parity meaning like basically
Even-
they're both
even
even,
in odds.
they're both even, or they're both odd.
Yeah, exactly.
Okay.
So for example, if we look, so maybe let's just play with examples. So if we have x equal, what is your favorite odd number?
Well, since they're both supposed to be odd, right? So we can just put like n is equal to do you want me to just a regular number, or do you want me to just do like 2n and then 2m? Make it more
Well, I mean,
abstract.
just take like concrete number.
All concrete numbers? Okay, so let's just make it 64 and 22.
I wanted them odd, so we're just gonna up depth a little bit, okay?
Oh, okay. Oh, you moved it up by 1. Okay.
Yeah, I wanted them to be odd, but
Okay.
so you have 65 minus 23, which is 42. which can be written as 2 times 21.
Okay.
So you see 65 and 23 would be equivalent
Oh, okay.
in a in equivalence relationship.
Okay.
Okay.
Hey, Jeff.
And basically, if you have so I'm just gonna write it in general.
Uh-huh.
Is an equivalence relation. Oh, I forgot something important. Relationship can only be defined on A times A.
Uh-huh.
Because you need to be able to make sense of reflectivity, and if A is not equal to B, it does not really make
So
sense.
basically it has to be an ordered pair of itself, right? Of the set, okay.
Yeah. Is an equivalence relation, then you can form the quotient.
Okay.
The quotient set. So, okay, let's maybe just introduce a notation. So if X is inside of A, we can consider the following set. So it's going to be all the A inside of A for which X is equivalent to A.
Okay.
And we call that the equivalence class.
Okay.
For example, in the example of the relationship with Tuzil, the one we just saw.
Yeah.
So basically, we would have only two equivalence class. We would have the equivalence class of 0, which will be all k inside of Z, such that well, if we want k minus 0 is equal to m maybe. Or in other words, if you want it to be more if you want to be more concrete, you just say, well, k is equal to 2m, right?
Yeah.
So this is the class of even integers. And you have also another class, which is the one class, right?
Okay.
So that will be by definition all the number such that k minus 1 is equal to 2n, right?
Mm-hmm.
Or if you prefer, you can rewrite it, so you just move the 1 the other side, so you just get that k is equal to 2n plus 1.
Which is the odd numbers.
Yeah. And you can show that this is only the two possible class. Okay.
Okay.
In the sense, if for example I take 3.
Yeah.
Well, so if I look at 3, it will be
K.
so k minus 3 is equal to m.
Uh-huh.
But as 3 is equivalent to 1,
Yeah.
you can actually check for yourself that this set on here will be exactly the class of 1.
Yeah, I think I can see why. Like, do you mind if I write it down?
Yeah,
So
if you want, you can see. Yeah.
Yeah, so I don't know if my thinking is in the same place. That's why I'm gonna try to write it myself. So let me just move a little bit to the side here so that you guys can see. So what I'm thinking is that since it's supposed to be minus 3, right? So if we rewrite it like this, it would be 2m plus 3, but you can rewrite it as that, and then you just basically reduce everything. Oop. would be 2m. Like that's what you meant, right? Because
yeah, exactly.
It's probably going to end up like that, and then like to I guess finalize it, it would be like basically, and then you can put like L or something.
Yeah.
To represent, and L is equal to m plus 1, which is an element of the integers.
Yeah. And now you're done because you know that every integers can be written as m plus 1 for some m, right?
Yeah.
So yeah, you showed that those two. That's very good. Good job, Peter.
Yeah, because like I think with odds and evens, I have the most fun with those type of proofs.
Yeah, and what you can do is, okay, so in general, if you have an equivalence relation of x, you can form a set which is called a quotient set.
Okay, so that's what that symbol means, right? Like the division symbol with the little equivalence. Okay, so this quotient set. Okay.
Oh, I think I cannibalize your.
No, it's fine. It's okay.
Your equal sign. I'm sorry.
No, it's okay.
So it's gonna be all the equivalence class of x.
Okay, so those, I guess those brackets are supposed to represent equivalence class, right?
Yeah. So for example, if you look at z quotient by the relationship we introduced before, we're gonna get two classes. The class of even integer and the class of odd integers.
Okay.
And usually, I mean, you sort of know those things without knowing, because this is the definition of z mod 2. So this is modular arithmetic. That's how we define
basically
like number mod 2, right?
Yeah, like so basically like the even numbers are like 0 mod 2, and I think like the odd numbers are like 1 mod 2. Is that correct?
Yeah.
I had to actually close my eyes to actually think about that. I was like, am I remembering that right?
And usually the idea is instead if you have z, you can do the same thing with n inside of 2. You will get this thing contains class of 0, 1, up to n minus 1.
So the one thing I'm trying to understand is like when you say it's equal to z, I guess divided by like 2z, right?
Yeah.
What does the 2z represent in this case?
So it just basically represents the relationship we have here. So basically this guy is not some very concrete notation, it's just a name.
Okay.
It's just a name for the thing on the left.
Okay.
So usually people will not write z quotient by this wave, because I mean they can have a lot of equivalence relationships. So to be a little bit more useful, they write, well, it's quotient out by 2z, and it's kind of implicit that the relationship is the one we define upstairs.
Okay.
So usually what you will have is the equivalence class of k will be all number inside of z, such that you can write x as qn plus k. You have to assume that k is between.
So is this the division algorithm?
Yeah, and pretty much the exercise I give you. Well, I assume that we have the division algorithm, but basically you can do the exercise with that.
So
and in the exercise I go a little bit more. I ask you to check that, for example. For example, it's kind of, we would like to have addition and multiplication on this thing, right? So you might say, I don't know, I have two classes, I don't know, 3 and I have 4. And maybe I would like to define addition, but I don't know what it is. So maybe one reasonable thing is to define it as such, right? But the problem is the 3 and the 4 are just like some element of the equivalence class. It can be replaced by other, right?
Oh, okay.
There's no canonical choice of 3 and 4, right? Like if we look at that mod, for example, if we're looking at that mod 2, I mean the 3 will be a 1.
Yeah.
and the 4 will be a 0. And the question is the equivalence class of 7 the same as the equivalence class of 1? Right? I mean, in the case of even and odd, they will be, but I mean, it's not obvious in general for a general n that it will be the case.
Yeah, it seems like it's talking about the properties of the numbers rather than the numbers themselves.
Yeah, so we have to make sure that this is well defined, in the sense that it does not depend on which which representation we took. Okay, and now I guess I have 5 minutes, so I'm gonna kind of leave you with a cliffhanger.
Yeah.
So with equivalence relationship, we can define the integers.
Okay.
As follows.
Okay.
So what we do.
Yeah.
So this is my third example. So we take we look at the Cartesian product of n with itself. Okay. That will be our set A.
Okay.
And we're gonna define an equivalence relationship on A.
Okay.
So what is gonna be? So we're gonna say that a pair of natural numbers are equivalent. And I will give you kind of the insight of what we want to do. So the problem is that we want to have positive integers, right? Negative integers, right?
Yeah.
To define the integers. I mean, that's pretty much, the natural number plus the minus part. But we cannot write minus, right? Because we don't know what it means yet.
Yeah.
So what we're gonna do is we're gonna do a clever way to write all the minus in terms of the plus. Okay. So when you see, for example, x1, y1, what we would like to think of is x minus y1. Okay, but we don't know what minus mean yet.
Right.
So what we're gonna do is we're gonna enforce some equivalence relationship that's gonna make this thing worse.
Okay.
So what we're gonna do is we're gonna say that x1, y1 is equal to x2, y2 if x1 plus y2 is equal to x2 plus y1.
Alright.
Okay. So maybe we can look at an example of that. So for example, if we have, 3 and 5, and we have 7 and 5. Wait, the other way around, 5 and 7. So you see, our goal in mind is to treat the parentheses as if they were like subtraction, right? So those two examples that I put at the bottom should be equal, right? They should be equivalent because, I mean, at the end of the day, they should represent the number minus 2, right? So let's check that. So this condition say, okay, takes the first component of this guy and add up the second component of the other guy. So it will be a 7. And the other guy will be, so the other part say, okay, takes the first component of the second couple, so it's a 5, and add up the second component of the first couple. So you get 10. So those two guys are equivalent.
Okay.
And basically, so we have to, I mean, I don't think I have time, but I leave as an exercise to check that this is an equivalence relationship. So you have to check that you have reflectivity, symmetry, and transitivity.
Okay.
And what we will have is that the quotient of this quotient out by our equivalence relation will be our integers.
Okay. So for the one you just assigned, basically find the equivalence relationship of this thing in the square or the rectangle.
So what I want to check is that this is a relationship. Equivalence relation.
Okay, check.
That's
if
indeed
it is an equivalence relationship. Okay.
Yeah. And okay, I don't really have time, but what you can, I mean, it's not really hard to see, but what you can do is that you can show that every equivalence class of this can always be represented as either n0 or 0n, or n inside of the natural numbers. Right?
Okay.
So maybe let's have a look at the example I had here. So so we had those two guys, but those two guys are supposed to represent the number -2, right? And the way we think of it is 3 minus 5, right?
Yeah.
So we can always put them in this form. So for example, we can have a 3, 5 would be equivalent to 0, 2. And if you have a 0 in your on the left, it means you're a negative number. If you have a 0 on your right, it means you're positive integers. For example, so if we just swap the order of this guy, it will be 2, 0.
Okay.
So that's how we're gonna build the integers.
So
but right now we don't have much. I just defined the set. We don't have addition, we don't have subtraction, we don't have inversion, we don't have another thing, right?
Okay. All right.
But I guess we'll keep that for the next time because I don't want to cannibalize your afternoon. So
it's fine. But thank you for teaching us all this. So basically, we just went from numbers to basically functions, but not in relation to like the operations mainly. So we just know the relationships right now, or just learned them a little bit. Okay.
Yeah. So right now, so on the integer, because the integer is not just a set, right? There's like addition, there's like subtraction, there's like a bunch of stuff.
Yeah, and when you said that at the end, I was like, oh wait, yeah, we haven't covered things like addition and subtraction yet. Yeah. And I just realized that now. Okay.
Yeah. But I'm not gonna do the addition from scratch. For example, I'm gonna just so in the natural number game, you already saw like all addition is defined.
Yeah.
So I'm just gonna assume that we have already defined addition on natural number. I'm gonna show you how we can extend it to the integers next.
So is it take it for granted that we just basically say that addition and multiplication are basically just obviously there? It's just that we have to like formulate subtraction and division, right?
So yeah, for us, we're gonna assume that the integers already have addition and subtraction and all the operation you want.
Yeah, and multiplication. Okay.
And next time we're gonna see how we can extend all of those on the integers.
Okay. All right.
You can already think if you want. You can already sort of think about how would you like define addition on those guys. I mean, probably a reasonable thing would be to add just the pair, right?
Yeah, because I'm just wondering, like, when you said the negative number is like equivalent to having like 0 in one of the pairs, or like
is 0 on the first component.
Yeah, I'm just trying to see how that works, because I'm like I kind of got a little bit confused about that.
Yeah, so there's stuff I have to show next time. So next time we're gonna show that first of all number can be written like that.
Okay. And
also this is unique.
Oh, this type of stuff is unique, right?
Yeah.
Okay.
And with uniqueness, we can pretty much do everything we want. So, for example, we're gonna say it's positive. It's the first number here is. I mean, if it has a 0 here and it's negative if it has a 0 here. You can define inverses. For example, if you have, I don't know, k which is given by n0, you can define minus k to be just the swap of orders.
So probably tonight I'll probably read more on relations and the equivalence relation, just to get a better clue. If you guys want to follow along with our journey here, you can probably read that up as well if you would like to know more about it. If you followed along so far. So Sascha, do you have anything to say to our global audience before we depart for today?
So I think I already told you about I'm forgetting my words. Famous mathematician with book analysis. Terran style.
Oh, Terran style. Yeah. I actually downloaded the first volume of that one.
Okay, I think in the first chapter, or at least the first chapters, he go through like the construction of the real number. If I remember correctly, he built the integers like the way we did.
Okay, so analysis 1, like first couple of chapters, right?
Yeah, so this can be a good reference if you kind of get stuck, because maybe I skipped some stuff because we're kind of time constrained here. We have like 4 hours in the weeks to get what we want. So so we have to. I sometimes have to squeeze some stuff. So
that's fine. Yeah. And
also it's also good for further reference. So if you have to review something, maybe it's a bit better here.
Yeah, absolutely. So, and also like like if you guys have the resources, like you guys can also like study while I'm off stream, like to like help better educate yourselves as well on the topic, because that's what I'll be doing throughout this whole week with Sascha's lessons. Yeah, and by the way, if you get stuck on the exercise, don't be shy to ask, right? For help. Yeah. So, guys, like, thank you for joining us today. It was a lot of fun and very informative. So, thank you, Sascha, for the lesson today. So, I will also be uploading this on YouTube. You guys can basically subscribe to my YouTube channel. If you're already watching this on YouTube, don't forget to hit a like, subscribe, and leave a comment down below. In case like Sascha, like if you want to add more to like what Sascha told us, like in case like you missed something, you can also put that in the comments down below. Also, for Twitch, I will leave the Discord, so you can talk to me. You can also talk to Sascha there. The assignments that Sascha puts, I will upload them onto the channel that says where is it? Assignments from streams. So if you guys want to get like the assignment that Sascha assigned, I already posted it there, so you can basically check out that on our Discord channel. So I think we will end it for there today. And you already said your final words, right, Sascha? Or do you have more to say? Oh no, I haven't said that to like and follow and subscribe on YouTube. Thank you very much, Sascha. The shame plug, I haven't pulled it. No, it's okay. It's okay. I do that to my friends all the time because they forget. But thank you for shouting out the channels. And also thank you for tutoring me and as well as Chad, if Chad is following along as well. So, he said his piece, so I will say mine. Always remember, guys, everyone is precious. You guys are just as precious as everyone else. And we will see you guys tomorrow for, I guess, like, the next lesson. So take care, guys. Bye-byes. See ya.